So that was cool. What's next? So the next thing, I think the second hyperparameter is called resolution multiplier. So we have resolution multiplier. So this is denoted in the original paper as rho. So rho does reduce the resolution of the input resolution to the architecture. So our rho is also in the range of 0, 1, but others provide some discrete values that are recommended for this hyperparameter. So what is the computational cost now? Computational cost. So by the way, if you by using the resolution multiplier, the computational cost decreases. So similar to the width multiplier, the computational cost decreases by almost rho squared. Right. So this is similar to the width multiplier. Now what we want is the computational cost, or the number of multiplications, given that we have used a width multiplier and a resolution multiplier. So the resolution should normally decrease the input resolution, right? So what represents the input resolution in this formula are these terms. So we have df. So we have just one term, it's df. So df represents the input resolution. So this means that we should multiply every df, each df in this equation should be multiplied by rho. And therefore, we get if we take also alpha into account, we should get the following equation. So we get dk squared times df squared. So df squared, this means that we should multiply this by rho squared times alpha m plus df squared. So this also means that we should multiply by rho squared times alpha squared m n. So this is the final computational cost given the hyperparameters the two hyperparameters we have used: width multiplier and resolution multiplier. So now if you want to make the model even faster or even smaller, there is something else you could use. You could remove, authors have suggested to make the model shallower. So shallow model. So what does that mean? So as the name suggests, shallow model means that the number of layers would be smaller, and therefore the model is shallower, right? So if you want to make the model shallower, authors suggest that it's better to remove 5 convolutional blocks, or 5 depthwise separable convolutional blocks, which have the following configurations. So they have 5 convolutional blocks. So in the depthwise step has the following kernel. So K1 has a width of 3 by 3. The number of these kernels is 512, and pointwise they use a kernel with the following configuration. They use 1 by 1 by 512. So this is the depth, or the number of elements, and this is the number of the kernels. So there are 5 convolutional blocks using this configuration. In other words, we have here 10 layers, assuming that each of these steps, depthwise and pointwise, are separate layers. So you can remove this and make the model shallower. So what's next now? I think I should talk about the experiments. So the key results that attracted my attention in the experiment section, so there are 5 key results. So the first, so experiment results, experiment key results. So these are the results I find interesting. There are 5 results I personally found interesting. So the first is, first authors have compared between alpha and rho, so width multiplier and resolution multiplier. So which one is the best? So from the table, this does not seem, there is no clear advantage of one hyperparameters compared to the others. It's not clear. It might need more tests, but when authors compared the width multiplier alpha, that is getting thinner model, with removing the channels I've just mentioned, the 10 layers, sorry, not channels, the 10 layers. This means that removing the 10 layers, so this would make a shallow model. So they found that thinner model is better by 3%, given that the number of computations is the same, of course. So you cannot say that it's just better like that. So the number of computations is the same, thinner model and shallow model, but the thinner model was 3% better. So I think that the alpha used here was something like 0.5. Just let me check this because I have the paper here. So I think it's the table 6. Yeah, so table 5. So table 5, narrow versus shallow MobileNet. So you could see that the thinner model has a 68% accuracy, whereas the shallow model has 65. So there is a 3% difference. So here the alpha is 0.75. So the alpha was rather 0.75. Also, comparison with popular models or architectures. So they have compared the MobileNet V1, so the baseline, there is no shrinking, with the VGG16, and they found that the VGG16 was 1% more accurate than MobileNet V1. So this is a trade-off. But MobileNet V1 was 32 times smaller and 27 times less compute intensive. So this is a remarkable result. This is really interesting. There is also a comparison with MobileNet. So V1, the MobileNet V1 baseline, was also more accurate than MobileNet and was 2.5, required 2.5 less computations. And what's interesting is that even with the reduced model, with the MobileNet V1, with the following reduction or shrinking hyperparameters, they used alpha of 0.5 and rho was approximately 0.7. So even with a shrinked model, MobileNet V1 performed actually, was more accurate than the SqueezeNet, more accurate than SqueezeNet and AlexNet, and of course it was much faster. So given these experiments, so most of these experiments were performed on the ImageNet dataset. So these experiments clearly show that the MobileNetV1 is a huge improvement in efficient convolutional neural networks. And what's interesting is that there is another version. So what we are discussing here is version 1. There is also another version called MobileNet version 2, which is also faster without reduction in accuracy. And it's also efficient in terms of its memory usage. So I think that I will discuss that in the next videos.